Hello, I'm Jonathan Kress from the University of New South Wales, and I'm going to show you how to solve one of the calculus problems from MATH1131. It's Chapter 6, Question 1. And Chapter 6 is all about inverse functions, and so I'll just give you a little bit of background first. In fact, I'll start with something from Chapter 1, the definition of a function. And functions are defined in Chapter 1. Here's just a few points that I want to make about a function. To define a function, f from a to b, you need the following things, and all of these things: the domain of the function, which is the set A, it's a set; the codomain, which is the set here, B, and it is a set; and a rule that takes you from a value in the domain to a value in the codomain, and only gives you one such value. And so the rule you might write like this: the rule takes x, which is in the domain, and gives you f of x, which is in the codomain. Okay, and without all of these things, you don't really have a function fully defined. So I've drawn some examples down here, or given the examples I've taken from the actual question we're going to do in a moment. Here's two examples, f and g. And f is a function which has the domain given by this interval here, which is all the real numbers from 0, including 0, going up and not ever ending. And the codomain is given here. It's the interval from 1, including 1, up to infinity, or never ending there. And the rule is supposed to be a description of how you get from a value in the domain to a value in the codomain. And here we're given f of x is the square root of 1 plus x squared. So if you take a value in here, so for example 0 is in here, and this rule tells you that you would the value you should get in the codomain is going to be the square root of 1 plus 0 squared, in other words the square root of 1, which is just 1, and you can see that really is in the codomain, so that's good. A couple of things to notice here. This codomain here, it just has to be a set that is large enough to contain anything coming out of the function f. In this case here, in fact, it's the smallest possible set of numbers that you could have, because if you made it any smaller, there'd be values in the domain that wouldn't be in here. And in that case, this is in fact also called the range. It's only called the range here because this set is as small as possible. If we had specified this function with the codomain being just all of the real line, which would have been a reasonable thing to do, then the range would not have been the same as the codomain. This is in fact the range. Okay, and I've drawn a picture here. I've indicated the domain across on the horizontal axis and the range on the vertical axis, and you can see that for, and this black line here is the graph of the function, and you can see that for any value in the domain, you go up here and then across, and you find that you get a value in the codomain. Okay, so another thing to note is that in fact this rule here would make perfectly good sense for some other values that weren't in this domain. For instance, you could make perfectly good sense of this expression here if x was minus 1. But because the function is defined so that its domain is exactly this set here, it doesn't include minus 1, we're not allowed to do that here. And that's an important, really important point, because if we did include some values over here and continued to plot the graph over that side, that would be a perfectly reasonable function to draw, but then there would be two values in the domain for every value in the codomain, and that would be a important thing to avoid if you want to be able to have an inverse function, which is what this question is about. Because for an inverse function, what you want is, if you start with a value in the domain, use the function to find a value in the codomain, then you must be able to go back unambiguously to the original value. If this function had been defined so you could put any real number into it, so the graph would continue over there, then if you had come to a value in the codomain, or and you wanted to know what value in the domain it came from, there'd be two choices. and you wouldn't be able to go back the other way. So there wouldn't be an inverse function. Okay, so the other example I've got here is the function g from the question, and it's got a different domain and codomain. In fact, they're the same sets as over here, but they're switched around. And so this is the domain here now, and this is the range. Sorry, the codomain. In fact, it's also the range. Okay. Right. Now the question is going to ask us to show that this function g is the inverse of that function f, and I'll come back to looking at these pictures again at the end. Okay, so let's just now tackle the question. It says, suppose that the functions f from 0 to infinity to 1 to infinity and g from 1 to infinity to 0 to infinity are given by these two rules here. F of x is the square root of 1 plus x squared, and g of x is the square root of x squared minus 1. Now we want to do part A is by calculating the composition of f and g on x and the composition of g and f on x, verify that g is the inverse of f. Okay, so these, in fact, if you look up the definition of what an inverse function is in the notes, you will see that what it's supposed to do is if you have a function f that takes you from its domain to its codomain, its inverse should take you back again. So if g is the inverse of f, then if you first of all apply f and then g, if g was the inverse of f, then you should end up back at x again. So both of these expressions here should come out to be just x if g is really the inverse of f. So let's just try and calculate that. Okay. So A, we want f of g of x. Now this means that, exactly this. It means that for x we first apply g and then we plug g of x into f. Okay, so let's just work this out. So g of x, according to our definition, is square root of x squared minus 1. And then f of x is the square root of 1 plus x squared, but we're now taking f of something else, so we put this in that pattern there. So it's the square root of 1 plus, and then the argument of f all squared. And now we need to just simplify this, and if you take the square root of something and then square it, you just get back what you started with. So let's just carry on over here. This is the square root of 1 plus x squared minus 1, which is the square root of x squared. And the square root of x squared, so this is actually the absolute value of x, but if we start out with a positive or 0 value for x, then this will just get us back to x again. So this is x, I'll say it's x for x greater than or equal to 0. And maybe we'll come back to that from part B, and just to see if that makes sense. Let's just calculate the other one now, having got what we wanted. G of f of x, this means g of f of x, and f of x is the square root of 1 plus x squared. And what does g do? G takes the square root of, first of all square its argument, subtract 1, take the square root. So we want square root of this. So we've just put this into there, where the x goes in there. And so this is square root of 1 plus x squared minus 1, which is the square root of x squared. Again, this is the absolute value of x. If x was negative and you squared it, the square root would give you something positive, but this is going to be equal to x, provided x is greater than or equal to 0. We might just, again, like I said, come back to that after part B, because part B asks us about the domains of these functions. So, provided the value we're putting in here, x, is greater than or equal to 0, we've shown that both f of g of x and g of f of x are both equal to x. In other words, applying g and then f gets you back where you started at x, or applying f and then g gets you back where you started. Okay, so now for part B, we just want to know the domains of f of g and g of f. And there's nothing really to calculate here, because provided f of g makes sense as a function, and for it to make sense as a function you need that the values coming out of g are things that you can put into f. So you need that the range of g is contained in the domain of f. As long as that makes sense, then the only restriction on the things that can go into this function is just the restrictions of whatever can go into g. And because we're applying g first, we must only put in values that g allows, in other words, the domain of g. So this is the domain of g, which is the interval from 1 to infinity, including 1. And the other way around, the domain of g of f is just the domain of f. Because to make sense of g of f of x, this function here works by first of all applying f and then applying g to the result. And the only restriction, as long as it makes sense, is that f, the things that can go into this have to be things that can go into f, and things that can go into f are the domain, things in the domain of f. Okay, so there we have the domains of these composite functions, and notice that they're different. But luckily for us, both the domain of these functions, only values that are greater than or equal to 0 are in the domain. So this was up here where we said this f of g of x and g of f of x was equal to x when x was greater than or equal to 0. Well, we're only allowed to put values greater than or equal to 0 into these functions, and so that's okay. Okay, so we've just shown that g is the inverse of f, and perhaps I'll just say, looking at these pictures here, you should also know that the graph of the inverse of a function has a nice relationship to the original graph, and that is that this graph here should be the reflection of that one in the line y equals x. It would be easier to see it if I drew these on the same set of axes, but you probably can see roughly from this picture that's the case.